Good afternoon, everyone. This is Mr. Couple. Today I'm with my IBSL Year 2 class, and we're learning about blackbody radiation, primarily the Stefan-Boltzmann Law and the Weins Displacement Law. So, without further ado, let's get started. So, the first question is, what is a black body? And usually, when I show this to students, they start laughing because it doesn't sound like a scientific term, but it actually is a scientific term. I mean, what are you guys' first thoughts when you hear that?
Uh, like a piece of matter that doesn't that absorbs like nearly all the light that hits it.
Yeah, it's exactly what it is. So the idea is like a black body is an object that doesn't reflect any light, so it appears black, right? So if there's no light bouncing off of it, then you're not gonna be able to see it, and you're just gonna you see and if you see nothing, well then that's black. So you nailed it, Alex. Now what I want you guys to realize though is like imagine that a black body starts to absorb energy. So that's what you're seeing in this animation. This black body is slowly absorbing energy. Well, as it absorbs energy, it's going to start to heat up and it's going to then start to radiate its own energy. So black body is actually they're really not black. They glow. So examples of this would be like a piece of metal when you heat it up and it glows, or like lava, or like a light bulb, or even the sun. So what is a black body? So it's an object that when you look at it, whatever you see is 100% coming from the object's thermal radiation. So it's not coming from reflections off the object or light that's bouncing off it. It's 100% all the light that you see from a black body is coming from the actual particles in the object jiggling around and releasing electromagnetic radiation. What questions do you guys have for me about black bodies?
So say we were never mind, that's a dumb question.
Are you sure?
Yes, I was just gonna ask what it would look like if we couldn't see the electromagnetic radiation, but
All right, then you would there'd be nothing there, right? It would just be black. All of
got
these
it.
pictures here, these are all black bodies. So every single one of these objects, when you look at them, they're approximately black bodies. I mean, there's no such thing as like a perfect black body, but all of these objects are approximately black bodies. And so that means when you look at them, you're seeing light given off by the object itself. So you're not looking at light reflecting off the object like a mirror. You're looking at light that's actually being generated by the object itself. And so that's what we mean by a black body.
So anytime you forge anything, it's a black body type substance.
Yeah, precisely. So here's the question. How does the type of material affect the color, right? The color is the frequency of the light emitted by the black body. So if we look at all these different materials here, you've got like tungsten in a light bulb. We have, I don't know what that is, some sort of metal in a stove. You've got coal, like in the charcoal embers. You got some metal down there. Maybe it's iron or something. You got glass, and then we have lava flow. Like, how does the type of material affect the color? So, like, what do you notice when you look at all these materials when they're all glowing? What type of material? How does the material affect the color?
It doesn't seem to. They look
The,
very similar.
Yeah,
no,
yeah,
the tungsten and the one in the bottom right are glowing a lot brighter
that's
than
true.
the rest of the other ones. Also, the glass has like designs in it, given the nature of glass.
Sure, like it's liquidy flowing around. But I think what Kelvin is touching on though is correct. I mean, you can see the same colors there. There's red, there's red, there's red, there's it's like red, white, orange. And so it turns out that this is actually what happens is as you heat something up, so as you raise the temperature, you'll notice that every single object, no matter what it's made of, no matter whether it's metal or glass or whatever, when it's heated, it will always emit light in the same order. So it'll start off as red, it'll get orange, it'll get yellow, and then it'll get white. So when you say something is white hot, that's like really hot. Whereas if something is just started warm, it's like red. And so this is the idea of a black body is like as the temperature raises up, you're going to see it go through these different phases of releasing different types of colors. If you plot this on a graph, it looks like this. So here we have the vertical axis is the intensity of the light. These are just arbitrary units, so we're not going to put down any like watts per square meter or anything. We're just going to put an arbitrary y-axis. But if you notice on the horizontal axis, we had the wavelength. And so the different wavelengths of light correspond to the different colors. And now what you notice from this graph is you should see that when the temperature is low, like 3000 Kelvin, this is the intensity of light. It's mainly intense over here in the infrared part of the spectrum. But as we heat it up, as we raise the temperature up and up, you can see that more and more of this distribution of light, the greater and greater intensity, is starting to lie in the visible range. We're starting to be able to see it. So when it's white hot, it's up here, like all the colors are being generated. But when it's glowing red, it's down here. So you're only seeing like the red part of the spectrum mainly. And so that's the idea of blackbody radiation. It's just really complicated formula. I'm not going to teach that to you guys. That would be like a college level thing. I'm not going to worry about that. The sun does the same thing. So the sun is a black body. And if you look at the radiation spectrum from the sun, you end up getting this picture here. So it's that same, you can see that same curve was being visible over here for the solar radiation spectrum. Okay, what questions do you guys have for me before I go over to the worksheet?
Apple, I don't know 3000 kelvins, much less 6000 of me.
That's cute. So we're good. I'm going to close this down. And then I'm going to say hello to everybody. Hello, here I am. And let's go find the worksheet. So I think I already loaded up. Yeah, here it is. Okay, cool. So hopefully you guys are able to print this out. If not, don't worry about it. But option A for the classwork for this assignment will be to complete this handout. And I'm going to work through it with you guys right now. So question 1 is what we just talked about. So the basic idea is that if objects are made of atoms and atoms consist of charges, and when you oscillate charges or you accelerate charges, they release light or they give off radiation, then that means that every object that has a temperature, that has particles doing this, that every object that has a temperature is going to be giving off or releasing energy, radiating energy. We call this thermal radiation. That's the answer to question 1. I'm not going to write it out. It's a waste of time. So I want to show you guys this. This is called the Stefan-Boltzmann Law, and it's how you can find the power that a black body emits. Now, actually, it doesn't have to be a black body because the E right there is called the emissivity. So I do want to talk briefly about what emissivity is, like what it means. So the emissivity, it's kind of like a percentage. It's a value between 0 and 1, and it just says how effectively a body radiates. So if the emissivity is 1, that means it's perfect, like it emits all the energy, perfectly emits it. Whereas if it's kind of not quite emissive, it could be like maybe 50% emissive, so like only 50% of the energy gets radiated. So the E is just some coefficient that's just going to tell us like how good the object is at releasing energy. But what you can see from the Stefan-Boltzmann law is that the power that an object radiates will be based on its temperature. And then, whoops, wrong pen. The power is based on the temperature, but then interestingly, it's to the fourth power of the temperature. So you've got this relationship that the power is directly proportional to the fourth power of the temperature. And all that other stuff over there will generally be constant. So A is the surface area of the object, and then E is the emissivity, how good of an emitter is the object, and then that, whatever that is, it called a sigma? I think that's a sigma, or is it a, yeah, I think that's a sigma, lowercase sigma. That's the Stefan-Boltzmann constant, and so that's just some proportionality constant that's just going to make the units work out. And then the value of that is 5.6 times 10 negative 8. All those crazy units, watts per meter, watts per square meter. What's up? Check. Is that Jordan? We can hear you.
What?
Is that Jordan talking?
Oh yeah, that's me. I thought I was on push to talk.
Yeah, you're not. We can hear you.
Oh, my bad.
Cool. Okay, so here are a few questions. Let's make sure we understand this equation. So the first question is, what is the power radiated by an object with an emissivity equal to 0? So what would happen if the emissivity, what would happen if that thing was a 0? Then what would we
It
get
would
out
have
for the power?
there would be no power.
Yep, so if P equals to 0, E equals to 0, then P equals to 0. So the body doesn't radiate at any temperature. So you could heat it up to, however high you want, and you would never be able to see any light. So this body radiates no light. So it doesn't matter how hot it is or how cold it is, it's not going to give off any light. Okay, what about if E equals to 1? So if E is equal to 1, then P is going to be?
It's just the rest of that equation.
Yep. Sigma area
A
t to the fourth
area.
power. There you go. And so we say that this is a perfect emitter. As it turns out, if you're a perfect emitter, it also means you're a perfect absorber. So I'm going to put a slash and put absorber.
How rare is this? Because like the one that radiates no light is pretty much impossible, right?
Yeah, I mean
How?
there's this material that researchers have been developing lately called like Vanta Black or something like that. Have you heard of that?
Yeah.
It's like this perfectly black. It's like as black as you can get. That would be like E equals to 1. But yeah, you're never going to get equals to 1 in a real life situation. I think even the sun is like not even 1. So, yeah. But there's no such thing as a perfect black body, so we just approximate things as a black body. And so that's what this next part here is going to be talking about. So I don't know if it's worth reading that or not. I think briefly I'll just talk about. So if E is 1, then we say that's a black body. So black bodies are this, it's theoretical. So notice like it says it's a theoretical body, which means they're not real. It's like an ideal situation. It is a perfect radiator as well as a perfect absorber. So black body absorbs all radiation falling on it, reflecting none. At low temperature, a black body radiates very little and absorbs all radiation falling on it, so it looks black. At high temperature, it radiates a lot and looks very bright. A very good example of this is a piece of charcoal. A real body is a good approximation to the theoretical black body if its surface is black and dull. So anything that has like a blackish, dull surface is going to act like a black body. So that's why charcoal is a really good example of a black body. Let's solve this problem. The emissivity of the naked human body is taken to be 0.9. So human bodies are 90% emissive, which means that if you shine light on a human, that we will absorb 90% and reflect 10%. So let's think about here. I'll just make my human look like this. Okay, there's my human. There's my human body. In this case, we'll be modeling the human as a sphere of water. Let's say. All right. So what that means is that your body temperature, right? So you have a body temperature of 37 degrees Celsius. So you're going to be radiating energy because of your body temperature. You're going to be giving off energy. This is called, heat vision. Like you can, like thermal, like through a thermal imaging system, you can see this. You can capture this light. But then realize also that you're absorbing energy from the environment as well. So you have some energy coming in. I'll draw that with these green arrows. So you're having some energy coming in, and then you're releasing, there's energy coming out. So we'll say that's the P in, and then you're also going to have some P out. What we want to figure out is what is the net P. So if you're just hanging out like in your room right now, it's like room temperature around your body. What's the net flow of power? Is there more energy going out of your body or more energy coming into your body if you're sitting in a room at room temperature? That's what we want to calculate. Does that make sense? Is the setup clear?
Yes.
Cool.
Yes.
So we'll say that our average surface area of a human is about 1.6 square meters. Like that's the area of like your skin all around your body. And so we'll take that as the A within the Stefan-Boltzmann equation. We'll treat ourselves as black bodies even though we're not, and so we'll model it as not a black body by using 0.9 for E. So what we'll find is that the P net, so the net power that we're going to be radiating, will be equal to the power that we emit. I call that the P in. So the power that we emit, I did that backwards. I called it P out. So the P out is what we emit, and then the P in is what we absorb. So we'll be absorbing some energy from the surroundings. That's the P absorb, and then we'll be emitting energy because of our body temperature. So we just need to subtract these two. So we're going to take the power that is releasing from our body and then subtract by the power that we're absorbing from the surroundings. So this is going to give us a net power equation. So I'll just call that P. Okay, now let's calculate. So the power that we emit is the Stefan-Boltzmann equation. So E sigma area times the temperature to the fourth power minus E sigma times the area times the temperature S to the fourth power. So now there, I'm using S to represent the surroundings. So we're looking at the emit, that's our body temperature, because that power radiated is based on us. Whereas for the absorb, that power radiated is based on the surrounding temperature. If we look at the next step, so now you can see that the E So the area that we're absorbing across is equal to the area that we're emitting across. It's the surface area of our body. All this stuff is going to be the same, where E over here is like the absorption rather than the emissivity, but they're the same thing, so you can just use them interchangeably. Anyway, what will happen there is the power will just be E sigma A times T to the fourth power of our body temperature minus T to the fourth power of the surroundings. So now we just need to plug in the numbers and then we're good to go. So the emissivity is 0.9. The Stefan-Boltzmann constant is 5.67 times 10 to the negative 8. And then we're going to put, I feel like, oh yeah, and then the area, what's up?
Did you freeze for anybody else? You frozen for me.
Careful, you're froze.
Okay, let me restart the stream. Thanks for telling me, guys. Discord's been having some issues today. They just rolled out a new like video chat feature, and it seems like their servers are kind of overloaded. So anytime that the video freezes, it's probably not you. It's probably Discord. Is it back now?
Yes.
Looks
Okay,
good.
cool. All right, so I'm just plugging in the numbers here. So emissivity 0.9, the Stefan-Boltzmann constant, or the coefficient, is 5.67 times 10 to the negative 8, and then the area is 1.6. So now we just have to plug in the temperatures, but realize that they need to be in Kelvin. And so the temperature of the human body in Kelvin, so that's
At
T.
273.
So we have 37 plus 273. And so that's going to give us 300 and I'm so bad at this.
10.
310. 310. Okay, so 310 to the fourth power. And then we're going to take the ambient temperature. So the room temperature is typically taken as being 20 degrees. So is that what I use? I'm trying to look at my notes.
I mean, you said about 300.
Oh, I did. I
And
put it
then-
right there. Duh. Okay, so it's not 20 degrees Celsius. So we'll say 300. So that's like the temperature in the room around you, about 300 Kelvin. And then you just plug all that in, and then what do you get? So if you calculate this power, so if anyone has, do you guys have a calculator? Do you want to do it, or should I just tell you the answer?
I do not have my calculator on me.
I'll just tell you the answer. It's 93 watts. So what does that mean? It means that, imagine you walk up to a light bulb and the light bulb is 100 watts and you feel the heat coming off that light bulb. Well, that's a very concentrated 100 watts of energy being radiated. But a human radiates the same amount of energy, about 100 watts. It's just spread out over a larger area. So you don't really think about us as being these little like heaters that are releasing all this energy, but we really are. The average human releases about 100 watts of energy in room temperature settings, which is pretty cool.
Keppel, that's funny because that's like the average for our body's temperature is 93 Fahrenheit, 94 Fahrenheit, around that. That's funny.
About 98.6 was our body temp, no?
Yeah, 93 is you're dead.
No, that's wrong. I literally my mom works in healthcare, and the fact is that the temperature we're finding that a human's temperature is actually lower than what it was measured back then.
Oh, that's weird. Yeah, I have no idea. Don't talk to me about biology. Get out of here. So that's just a rough calculation. After I'm done recording the video, if you guys want to stick around, I'm going to do a calculation of what if there was no P in? So like what if you were just like, floating in space. So there is no power coming in. You were just floating in space. There's no direct sunlight or anything like that. You're just like in the dead interstellar space. Then about how long would it take you to lose enough energy that you freeze? I'm going to do that calculation after the stream's over. And I'm going to show you guys a clip from Lost in Space because I can't put it on YouTube because I'll get a copy strike violation. That'll be the after the stream bonus for you guys that showed up today. All right, let's see. Okay, next. So we're going to talk about this thing called Weins Displacement Law. So I already showed you guys this graph. So this is the graph of the intensity against the wavelength. And what we see is that the peak of the graph is shifting leftward. So as we get hotter and hotter and hotter, as we rise the temperature, the shift of like that maximum wavelength, like the peak intensity, shifts to lower and lower wavelengths. So this is called Weins Displacement Law, and it's really cool. So let me explain what we're going to do. Okay, so we're going to use this equation, and we're going to calculate the peak wavelength emitted for various objects. So the thing is, like, realize you're not going to be getting. I'm trying to say the distribution of wavelengths, like when light is being released by a blackbody, it's releasing light across all the different colors, all the different wavelengths you can imagine, but it's at different intensity levels. So what we want to find out is, like, what is the brightest light? Like, which color or which wavelength is the brightest? And that's what this equation will tell you. Human body has a temperature of 37, average Earth surface is 288 Kelvin, and the temperature of the sun is 5800 Kelvin. It says calculate the peak wavelength of the emitted radiation for each. All right, let's do this. So for the human, we're going to use Wien's displacement law. So basically, we just need to divide by t on both sides. So that's how I'm going to write it down. So I'm going to say that the peak wavelength, so lambda max, will be equal to 2.90 times 10 to the negative third, and that's Kelvin meters. Kelvin meters is like a weird unit, but that's the unit. Kelvin meters divided by the temperature. So for humans, 370, 30, or what am I trying to say? We just did it over here. The 37 Celsius is about 310 Kelvin. So I'm going to put 310 Kelvin down here. And now you can see why we had such a weird Kelvin meter unit. So that way the Kelvins would cancel. And so we get that the peak wavelength of the human body that we emit at, so like you won't be able to see this. This wavelength is too large for your eyes to see because it's in the infrared part of the spectrum. So if you do the math here, you get 9.4 times 10 to negative 6 meters. And that's in the infrared. So if you want to see the light that your body is giving off, like if you actually want to be able to detect it, you're going to need to use an infrared camera. And then you'll be able to actually see, like if you looked at a human with an infrared camera, the human would appear to glow like a light bulb. But we don't see glowing humans normally because the peak wavelength is in the infrared. So you're not going to be able to see any light coming off of a human. We're just not hot enough. You're like, I just thought of like a funny joke. You'd be like, baby, you're so hot, I can, like, you emit in the visible. Sorry.
Keppel, strain yourself, please.
Oh no, I'm on recording here. I got to be careful. Okay, let's do the same thing for the Earth. So let's find out at what wavelength does the Earth primarily emit at. So we'll put in the surface temperature of the Earth, which is 288 Kelvin. And then you might be thinking, why are we doing this? Like, this is very similar to the one we just did above. Yeah, sure. But the reason is because the next part of this unit is going to be talking about enhanced greenhouse effect. And it turns out that this wavelength of 1 times 10 to the negative 5 meters, which is also infrared, that this peak wavelength actually ends up being the exact right number for carbon dioxide and other greenhouse gases to absorb at their most efficiently absorbing at that same exact wavelength. And so the light that the Earth gives off happens to be for the temperature of the Earth happens to be the exact wavelength that is absorbed by greenhouse gases. And so that's what creates that, layer of insulation around the Earth that is able to absorb the heat and then reflect some of, or not reflect, but re-emit some of it back down to the Earth, keeping us warmer than we should be. And we'll be talking a lot more about the enhanced greenhouse effect next week. The last one I wanted to do was let's calculate what the maximum wavelength is for the sun. So we'll do the same thing. So 2.90 times 10 to the negative 3. I'm going to stop writing units because I'm getting annoyed. And I'll put 5800 Kelvin on that one. Okay, so if you do this math, you get 5 times 10 to the negative 7, which is 500 nanometers. That's visible. That's what's like green or something like that. That's in the visible part of the spectrum. Might be orange. I don't have my Roy G. Biv wavelengths memorized. And so that's why we can see the sun, because the sun is much, much hotter. And so when you increase this temperature on the bottom, you end up getting a much smaller wavelength, and you get down into the visible part of the spectrum where our eyes can actually see it. You guys have any questions about that? I'm going to pull up that other image. It was better than this one. Let's see, it's this one. So you could see that dot right there, that's the lambda max. And so that's what this equation is calculating. It's calculating the lambda max. And so you can see that as the temperature increases, we go hotter and hotter and hotter, the lambda max is shifting to get shorter and shorter and shorter. So it's starting out in the infrared when you first start to heat something up. Its peak is in the infrared, which is why you can't see things when you first start to warm them up. But then as they start to get hotter and hotter, most of that intensity starts to become visible to us. All right, I think I'll keep going. Number 5, it says the longest wavelength visible to the human eye is 740 nanometers, which corresponds to the color red. Part A, calculate the temperature of a body that emits light with a peak wavelength of 740 nanometers. So let's figure out how hot does something need to be in order for us to see it, in order for the light that it releases to actually be visible. So we want to do that calculation. All right, so what we're going to do is instead of solving for lambda max, we're going to solve for temperature. So you can see that the temperature is just that constant divided by the wavelength. So we're going to take the temperature. So the temperature is going to be that constant, so 2.9 times 10 - 3 Kelvin meters divided by, and now we'll put in the visible wavelength, which is 740 nanometers. And so if we do that calculation, it ends up being 3,900 Kelvin. So you're not going to be able to see something glowing unless it's thousands of degrees hot. So you will not be able to see your human body glow because we're just not hot enough. But if you get hotter, like the flames of a fire or a light bulb, when the temperature goes up, you can start to see the light that it's giving off. What questions do you guys have? We good? I feel like you guys haven't talked in a while, so I'm kind of getting nervous.
I was curious earlier, so I looked up 500 nanometers, and it is green, and I think that's why plants evolved to... Wait. Never mind. That doesn't make sense because they
Tell me why it doesn't make
reflect
sense.
green light.
Yeah, they do.
And so that doesn't make any sense. So I don't know why they evolved to reflect the most, or
Well,
the
Well, think of it like this, Joel. Like, what would be the most efficient mechanism for a plant? It would be to absorb all wavelengths. So what color would be the most efficient for a plant?
So wait, all of them. So it would absorb all wavelengths, meaning green, or
No, it would be black. That would be the most efficient leaf.
oh,
Right? The most efficient
okay.
leaf would be black because it would absorb all the light that hits it. It would get getting all the energy. Now, I don't know the exact answer to this question, but you could look it up. There's tons of YouTube videos about it. But I think it's because of the chemistry that actually happens within photosynthesis. Like it happens at certain frequencies, and like green ends up being one that it doesn't happen at. But I don't know the exact answer to that. I should only recommend that you search it up. It's a really cool answer. I think the physics girl had a video about it once. I'll see if I can find it. I'll link it to you guys. I just don't want to say something wrong because I don't remember and I wasn't prepared to talk about it. Okay, here's a question. So if this is the temperature that something needs to be in order for us to see it, then why can you see a candle? Because here's the thing, guys. A candle, the temperature of a candle is only 1,700 Kelvin. So how can we see a candle if it's way below this limit that we just calculated? It's way colder than 3,900 Kelvin. So why are we able to see a candle even though a candle is way colder than that? Thoughts?
Is a candle not a black body?
We'll treat it like one. That's okay. Okay, so here's why. We got to go back to this graph. I'm going to project the better one, this one. I don't like this one because I can't draw on it. Well, I don't. What am I going to say? I'll just use this one. The numbers are going to be wrong, so let me remove the numbers. Wait, I removed too much. Let me get rid of all these numbers here. Okay. All right, so let's say that your candle is here. So that's your peak intensity of the candle. But visible is over here. So this is where things start to become visible. So your peak is very clearly in the infrared for your candle. But notice that not all of the light is infrared. There's a very tiny bit out here of quote-unquote white numbers. There's a very little bit of visible. So this is where the maximum, right? So we calculated that the maximum would be shifted into visible at that 3900 Kelvin, right? That's if you were at 3900 Kelvin, you would be like this, right? So I probably did that wrong. Let me try one more time. So then that would be 3900 Kelvin. Well, a candle is not 3900 Kelvin, so we can still see from a candle because the maximum is infrared, but that doesn't mean that all the light is infrared. There's still going to be a little bit of visible light that it's giving off. So that's the answer to that question. I'm going to leave that blank. I'm going to let you guys answer that. I'm going to also leave number 6 for you to do as well for practice. I don't want to do everything for you guys. But that's it. I'm going to end the video here. Hope you guys enjoyed this. Stick around. I'm going to be doing the cool calculation and showing you guys a clip from Lost in Space. All right, take care. Have a good day, guys. Bye.